New. And hopefully it won't stop after 20 minutes. For now. All right. Hopefully this will not evolve into a read my mind exercise. In this scenario, I have a box cleverly called A moving to the right, and I have a box B moving to the left. They are going to collide. Let's just say they're going to collide at this spot right here. They're going to collide, boom, boom. That's when they meet. They're going to compress slightly, and then they're going to bounce apart. Actually, I want to draw that a little bit differently. That's when they meet. They're going to be together like that. They'll move slightly, and then they will separate. So, while the two objects are in contact with each other, there are three things that are the same for both. Three things that are the same for both objects. Three quantities, in theory measurable. What are the three? Now, just to add an air of excitement, do a little hangman. All right. What is a quantity that will be the same for both objects? Quantity being something for which we could associate number in units if we had to.
Force.
Be more specific.
Newtons. Yes. Newtons.
Sorry.
Newtons.
Oh, the same number of newtons?
Yeah.
So same magnitude of force.
Magnitude of force.
Okay. Magnitude of force will be the same. Or magnetide. That Newton's third law, A will push on B with the same amount of force as B pushes on A.
Acceleration.
Not necessarily. It depends upon, even though the magnitude of force is the same, if their masses are not the same, then the accelerations would not be the same.
The force of them pushing away from each other, bouncing off of each other,
You're saying the force would be the same?
maybe.
I was waiting for you to commit to something.
I guess. Yes.
All right, thank you for committing. The forces will not be the same. Why will they not be the same? Sorry?
Opposite direction.
Absolutely. That's it. So even though the magnitudes are the same, the force, the vector force is not that poor balloon.
Like normal force? And they hit each other?
You mean the same, it would be a normal force magnitude of, I'm going to put normal in parentheses here because it really doesn't matter which force that is So at this point, I think we've covered forces. All right, besides forces, if you mention force, we'll just add another part over there. So don't mention forces, we're done with those. Magnitude's the same, directions are opposite. All right, what else? What other quantity is the same? And I will give a hint that one of them is so incredibly obvious, most groups don't think about it.
The type.
Sorry?
The type.
Type?
They're both boxes.
Oh. True, I was not thinking of that. Mass A and Mass B, I guess I called them boxes. Yes. I'm not going to put that one down because they don't have to be.
That means size doesn't matter either.
Right. So I don't.
So weight doesn't matter either.
Pardon?
Weight.
You're asking if weight matters or if weight is the same for both? Weight is not necessarily going to be the same for both. I've given you information about mass, and what I'm asking is does not have anything to do with the mass or weight.
Speed.
Sorry?
Speed.
No, they're coming at each other. If they were traveling the same speed, they would have connected directly in the middle, between them. It's smack dab in the middle, so speed is not the same for both.
The distance they meet each other, because B is going the farther distance than A is, but A pushed over the line.
All right, which distance are you talking about?
Uh,
You're talking about that the distance that A traveled.
is shorter than the distance that B traveled.
I'm looking for things that are the same move. Whether A moved more or less, not enough information is given, but it's implied A does not move as far.
Would it be velocity?
All right, right off the bat, when we go from here to here, which way is, well, I guess they're both going in the same direction at that point. When they first meet, actually going from here to here. So at this point they meet, they both move to the right, but at this point, at some point they bounce apart and A moves off to the left, B moves off to the right. There will be a point in which they will not be going in the same direction. Plus, if their initial velocities are not the same, you can't make the guarantee that the velocities would be the same the entire time. Notice with the oversized head like that, it's my cousin Robert. And Robert, if you're watching, congratulations on actually taking an interest in education. Think through what are the quantities? Things we've associated to numbers.
Friction.
What I say about forces.
Oh, yeah. That's right.
Displacement.
All right. Just throwing a random word out there. It actually, while they are touching. So A goes from here, basically from here to here. B goes from here to here. The displacement should be somewhat the same there. So displacement.
Oh. How about tension? That's a force.
What did I say about forces? It's not a monocle. The last one, is the one you haven't thought of, is the one that's so incredibly obvious that people don't think about it.
Position.
Pardon?
Position.
said position. They are clearly not in the same position. Generally, when you have a mass like this, when you say position, you're talking about the position of the center of mass. So that would be here and here. Those are not the same position. The change in position is the same, but the position itself is different.
Did we already say direction?
The direction of what? Well, we've got various vectors. You might want to just stop before we add more body parts on that one. All right, here's my obscure clue that I've had only one student from another reference. I'll do it anyway. Hint, it's the name of a Bobby Sherman song. I did have a student who had actually been to a Bobby Sherman concert. Obviously, an older student, because Bobby Sherman was popular in the 70s. His sister was a fan. He insisted he went because of his sister.
We still have the nose on the mouse, right?
We'll find out at what point we give up. I believe it's also the name of a Pink Floyd song. So we got one Pink Floyd fan?
Yeah.
And it's not Hypers at the Gates of Dawn.
That was on my phone. They're Pink Floyd songs.
Is it momentum?
So we're going beyond the chapter. It's a quantity that we have dealt with before.
Well, we have mentioned momentum.
Yeah. Well, momentum is coming up, as is energy, so leave momentum and energy out of it for the moment. I will connect it just when we're finally done.
We still have the hair braid.
And the toes and the fingers, we got more than, I guess in regular hangman, there are only 26 possibles. I guess if you do Greek, uppercase, lowercase, got 100. I guess it has devolved into a read my mind exercise.
I would say.
Well, think about the stuff that we've covered already. What hasn't been mentioned?
The time that okay, yeah, that's what I would say. The time that they hit is the same.
No, not the time that they hit, because they could be starting with different spots.
The time that they
Start each other.
From the moment they touch to the moment they separate, they touch each other for the exact same amount of time. That is the same.
So what's the song?
Bobby Sherman song. Is it a Pink Floyd song, Ty?
I don't know, I can't remember.
Okay.
I haven't listened to it, so.
If you ever listen to it, if you're thinking, Bobby Sherman, I wonder if he's any good. Yeah, they didn't have the voice you're hearing is actually his. They didn't have all the electronic stuff in order to improve it in the recordings. Anyway, so what does this have to do with anything? All right, we've already established magnitude of whatever force they're applying to each other is the same. They are in opposite directions, as was mentioned. I'm going to write, this is basically Newton's third law, this first bit. I'm going to write that in shorthand notation. We don't need this anymore, so I'll put it over here. That one there. The force that A exerts on B is equal to, actually, sorry, typical notation. This is the force that B exerts on A. Force B exerts on A is equal to the negative of the force that A exerts on B. All right. That's just the shorthand notation from Newton's third law, the stuff that I had written right there, the stuff that we've done since we started doing forces that come in pairs and so forth, just shorthand. And this would be the force on B from A. Now, if I combine it with the idea that they touch each other for the exact same amount of time, so if I have that the time that A is involved in the interaction is equal to the time that B is involved in the interaction, if I bring these two together, combine these two ideas, we get to this idea of momentum, as mentioned earlier, and impulse. If I bring into the idea of displacement into it with force, if I bring these into concept, we get into this idea of energy and work. So we've got momentum, impulse, energy, work. This is chapter 6, and this is chapter 7. We've gotten the foundation of all of it, and now what's left is to, are there different ways of looking at the exact same thing? And then we'll get into other orientations. We'll get into things that might rotate, because we've only dealt with things moving in essence in a straight line or a circle. Bless you.
Thank you.
So, I am going to, actually there's a video for it, I'm not going to subject you to the derivation. I do recommend that you go through, watch the video on the derivation, mainly because I get sort of tired in textbooks where they go, here's the formula, here's how you use it, as opposed to where does this formula come from. So part of the derivation, I do get into why momentum is what it is. So I am going to do here's the formula for momentum, this is what it means, but please watch the video in order to know why this is the formula. First off, the symbol for momentum, of course, is a P. Because why not? I have seen videos out there where they ask the question, why is it a P? And they often answer, I don't know. I forget. I actually have seen it. It's from the Latin or the Greek, which is, if in doubt, going to be the answer. So that's momentum. That's equal to mass times velocity. I've heard some physicists try to justify that, how does one object get from one point to another, and they try to use momentum as their reason. To me, momentum is just a math convenience. Because it turns out, if I take the force on A from B, and I multiply it times the time that they're in contact, that's going to be equal to the negative force on B from A times the time they're in contact. So all I did is those two are equal, and I just multiplied both sides by it. Because again, the math people tell me is if I multiply both sides by the same thing, it's still valid, or it's as valid as it was before. It turns out that this, again, watch the video, is equal to the change in momentum of A. And this is equal to the negative change in momentum of B. This mass times velocity. If I just add this to the other side, so I'm just going to add that, bring it over. What this says, and this is an incredibly important concept, this is again just the math version, because who doesn't like symbolic language here? Whatever change happens in the momentum for A, plus whatever happens to the change in momentum for B, that total change is 0. So we start out with a certain amount of momentum. After they interact, the total change is 0. Momentum is conserved. This is the momentum, or let's put it in the more complement form. This is known as conservation of momentum. Slightly different form. My initial momentum is equal to the final momentum. You're working on your Nobel Prize winning work in physics. You will be probably using this. It all stems from Newton's laws for force and time. Now, I take this marker. It has some mass. Hopefully you'll agree. What is its velocity at the moment?
0.
Therefore, what is the momentum of the marker? Okay, so just mass times velocity. Velocity is 0. Momentum is 0. All right, no momentum. I let go. Did momentum stay 0? So what is this about conservation of momentum when I said momentum would stay the same? If that gained momentum as it fell, something had to have countered that. Velocity increased, but velocity, what object got momentum that was countered by that? Say it again?
The ground.
You didn't feel the earth rush up? The earth moved. Matter of fact, if I stood on this desk and stepped off, I would fall, the earth would come up to meet me. Now, how far does the earth move? It's a massive object. Applying 220 pounds of force isn't going to do a whole lot. I've calculated before, and the earth moves basically the size of the nucleus of an atom. That's how much it moved. It's enough for physicists to go,